Welcome to my new calculus channel. My name is John Gabriel, and if you'll recall, we were discussing the fact that there are no axioms or postulates in sound mathematics. So in the previous episode or video, we derived all the four requirements, the first four requirements. That is the straight line, the extended line, the circle, and right angles. And so, okay, I seem to have left a little part out between the straight line and the circle here, but basically that the straight line can be extended. It's actually very important because without that requirement, you can't properly define a circle. So we covered all this information, and of course, from point, before we could get to a straight line, we had to define all these concepts: motion, direction, path, and so on. Now, I want to now continue in this video to show you how we derive parallel lines. Now, if you look at book 1 of Euclid, definition 23 just says that parallel lines are lines which do not meet in either direction, if extended in either direction in a plane. Okay, so that's a very loose definition, and of course, Euclid didn't actually show these definitions, derive these definitions from the circle, which he should have. For example, he talks about angle before a circle, and that's not right. We get the idea of angles from a circle. Like I showed you earlier, where I told you that an angle is defined as the length of an arc over the radius, and that if we place a triangle with one vertex at the origin and one side on the radius or diameter, then we'll be able to see that that angle has a measure in terms of radians. Okay. Now, also another thing I wanted to tell you is that this definition of angle here gives you a unique angle for every angle in the circle, because as you can see, the arc length changes all the time. Okay, it's not the same. It starts at 0 and it goes all the way up till 2 pi. All right, so that was the definition of angle. And now, to define parallel lines, what we need to do is continue with our circle, but we need a few more definitions, and we'll start off with the concept of a chord or a secant. So what is a chord? It's just any straight line that has endpoints which lie on the circle circumference, okay? And now we are in a position to define what it means for lines to be parallel. So we'll say this, that if the arcs formed by a chord on either side of a perpendicular between the chord and a diameter are equal, in other words, symmetrical, as I'll show you now, then the chord is parallel to the diameter. So what we're talking about now is this. If we have these two arcs here, which are equal in length, all right, and we know that by symmetry they will be if this line here is resting on two arcs of the same length, and of course we've already defined a perpendicular, so we can see clearly that a parallel line or parallel lines can be defined this way. In other words, this line here is parallel to the diameter if it rests on the same arcs, okay? And that's very easy to see, isn't it? All we have to do is just move along the perpendicular, which we've already defined. So as you can see, there you have parallel lines. There's nothing to believe in. There's nothing to accept on faith. I've shown you how to derive all of these things from nothing. And that's really all that there is to it. So you can establish in a rudimentary fashion that if two straight lines are parallel, either straight line must coincide or at least partly overlap the diameter, and the other over a circle, chord, or secant. Okay? So now we are ready or in a position to talk about the fifth and the final requirement, which, by the way, has nothing to do with parallel lines. And contrary to all the rot you've heard, the fifth requirement is really a requirement that deals with another property of a transversal. And I'll show you what that means in a moment. Okay. So now, I think I can finish in this video, and I'm going to try to do that, but if not, I'll finish in the next one. We can define a transversal as a straight line which meets any secant line and diameter in different points. Okay. So here are different examples of transversals. The red line's transversal, the blue line are chords, and the green lines are diameters. And we can call the point where the two lines of an angle meet a vertex, since we also want to talk about angles not at circle centers. But it doesn't matter if they're not at circle centers, because they could always be at a circle center. So given that any two parallel lines and a transversal crossing them, we need to give names to the angles formed. Now pay very careful attention here, okay, because this is really important. We call this red angle and this purple angle supplementary angles, okay, because they lie on the same side of the transversal between the two lines that are crossed. They're not necessarily parallel, okay, they don't have to be parallel. The dark blue and green angles, denoted by these dots here, are also supplementary angles because they lie on this side of the transversal. Now, finally, the black and purple angles, this black and purple angle, are called corresponding angles. And what we need to do now is show that pairs of corresponding angles are equal and alternate and so on. And we'll do that next. So to prove that the black and green angles are equal, to prove that this and this angle are equal, it is easy because a circle with a center at this light blue point that you see where I'm pointing here, has the same radii, and by symmetry, the arcs on which the blue and the green angles are subtended. Okay, so that's how you can show that the black and the green angles are vertically opposite, and hence that the black and purple angles are corresponding angles. So we can show similarly that the black and purple angles are equal because of two equal centers at the light blue point. So if you put a similar circle with this center here and another exactly similar circle at this center here, then we can see that the black and purple angles are equal. So we've established names for the different kind of angles. And of course the alternate blue and purple are equal because they are both equal to the black angle. Okay? So we know that the sum of supplementary, and now that's a new term, is the same as two right angles because we showed this earlier. Now if by the way, the same as two right angles has nothing to do with a number even yet. We established that on a diameter we have two equal arcs, and those are what right angles are subtended on. So if the light blue points are centers, the result is immediately evident. You can read all of this slowly in the presentation. Moreover, we can prove that the sum of supplementary angles, say the red and the purple, is equal to two right angles because the purple angle is equal to the green angle, they're alternate, and the green and the red angles are supplementary. So now we have established everything we need to deal with the fifth requirement. So I think I'm going to stop here, and I will deal with the fifth and last requirement in the final video, which is to come. So if you're not already a subscriber, please do subscribe to my channel, click like, and tell your friends about it and spread the news. And as you can see, we've derived the four requirements plus parallel lines long before the fifth requirement, and we're going to also see that we need to derive some more prove some more information before the fifth and last requirement, but I'll save that for the next video. I'm John Gabriel, and this is the New Calculus channel. Till next time, goodbye.